Now, this is our second chapter, Maxwell's Relations and Applications. In this chapter, we will see the ideal gas equation because we have to use ideal gas equation at various equations. Consider 1 mole of ideal gas. The equation of state can be written as for 1 mole of ideal gas. We know that what is the ideal gas, that is PV equal to nRT, where n, small n is the number of moles. For 1 mole of ideal gas, the equation becomes PV equal to RT, where R is the universal gas constant. Okay. Therefore, from this equation we can write P equal to RT upon V. Now differentiate this equation with respect to T, taking V as constant, where T is the temperature and V is the volume of the gas. Therefore, we get del P upon del T equal to R upon V, because T is constant. Because V is constant and differentiation of T with respect to T, that is equal to 1. Therefore, we get del P upon del T equal to R upon V. Again, if we differentiate this equation with respect to V by keeping T constant, therefore we get del V of del P upon del T equal to minus R upon V square, because differentiation of 1 upon V is minus 1 upon V square. Now again, from equation we can write, if the volume changes, temperature remaining constant, that is del P upon del V equal to minus RT upon V square. We have taken the equation number 2.1 and we have differentiate that equation with respect to V. Therefore, we get del P upon del V equal to minus RT upon V square. If now the temperature changes, the volume remaining constant, therefore we get from this equation, differentiate this equation with respect to T, then by keeping volume constant, therefore we get del T of del P upon del V equal to minus R upon V square. And now compare two equations, equation number 2.3 and equation number 2.5. What we get, del 2P upon del V del T equal to del 2P upon del T del V. It means that if we differentiate pressure with respect to temperature by keeping volume constant is equal to differentiation of pressure with respect to volume by keeping temperature constant. It means that differentiation of pressure is a perfect differential. Similarly, we can also show that the dV and dt are also the perfect differential by using the same equation. By using the equation PV equal to RT, we can write V equal to RT upon P, and by taking the differentiation of V with respect to T and with respect to V by keeping one other variable constant, we get the same equation. Now we have to see some thermodynamic functions. We know that what is thermo. Thermo is the temperature and dynamics is the motion. Therefore, according to first law of thermodynamics, if the substance absorbs dq amount of heat, part of heat used for doing external work and remaining part of heat is used to increase internal energy of a substance. Suppose we have some gas in some volume and we have providing the heat to that gas. Suppose that gas absorbed dq amount of heat. Therefore, according to first law of thermodynamics, dq equal to du plus p dv, where u is the internal energy, p is the pressure, and v is the volume, and q is the amount of heat absorbed. Again from second law of thermodynamics, we have the equation dq equal to t ds, where t is the temperature and s is the entropy. You know that what is entropy? Entropy is the disorder in the system. Disorder by changing the heat of the substance, there is the disorder in the it means that suppose the molecules are moving in a straight direction, in straight line. By absorbing the heat, they will move random motion. There is a disorder in the system. Therefore, where ds is the change in entropy of the substance when it goes from one state to other. From above equation, TDS can be written as du equal du plus PdV, because we have from above two equations, left hand side equal, therefore right hand side should be equal. Therefore, we get TDS equal to du plus PdV. Therefore, du equal to can be written as TDS minus PdV. This equation gives the change in internal energy of substance in terms of four thermodynamic variables: pressure, volume, temperature, and entropy. That is, du is the change in internal energy of the substance, T is the temperature, ds is the change in entropy, P is the pressure, and V is the change in volume. The properties of pure substance are conveniently expressed in terms of four thermodynamic functions. One is internal energy, other is second is Helmholtz function, which is also called as Helmholtz free energy, which is represented by F, which is equal to U minus Ts, where U is the internal energy, T is the temperature, and S is the entropy. Third is enthalpy, which is represented by H, which can be written as U plus PV. And fourth is Gibbs function, which is represented by G, which can be written as U plus PV minus Ts, or it also can be written as H minus Ts, because U plus PV is H, enthalpy. Now we will see first thermodynamic function, which is internal energy. The internal energy or intrinsic energy is the total energy of the substance. According to first law of thermodynamics, we have the equation dq equal to du plus pdv. Second law, we have the equation dq equal to tds. Therefore, we get equation du plus pdv equal to tds. Therefore, du equal to tds minus pdv. This equation gives the change in internal energy of the substance in terms of thermodynamic variables: pressure, volume, temperature, and entropy. Internal energy is called first thermodynamic potential. It is called as first thermodynamic potential. All the four thermodynamic functions also called as thermodynamic potentials. Therefore, it is called as first thermodynamic potential. Now, suppose in the process of changing heat of the substance, suppose there is a process of adiabatic process, and we know that in adiabatic process, suppose we have the gas in a container of volume, suppose V, and adiabatically it changing from one state to other state, and we know that in adiabatic process no heat exchanges by the system and surrounding. त्या सिस्टीम आणि सराउंडिंगमध्ये कोणत्याच पद्धतीचं हीट एक्सचेंज होणार नाही. इट मीन्स दॅट चेंज इन हीट शुड बी इक्वल टू झिरो. देअरफॉर फ्रॉम फर्स्ट इक्वेशन वी कॅन राईट, या इक्वेशनमध्ये जर आपण डी क्यू इक्वल टू झिरो जर पुट केलं तर आपल्याला मिळते डी यू इक्वल टू मायनस पी डी व्ही. In this process, the work is done by the system at the expense of its internal energy. Here we can, from this equation we can see that here du, change in internal energy, equal to minus pdv, pressure into change in volume, that represents the work done, on the system or by the system. But it is negative. It means that the work is done by the system at the expense of its internal energy. It means that the internal energy changes, which is the part of internal energy, that is the change in internal energy. It means that the part of internal energy is used for doing some work by the system. Second is for an isochoric adiabatic process. Now we know that in isochoric process volume remains constant, and it is isochoric adiabatic. It means that adiabatic means no exchange of heat by the system, between the system and surrounding. It means that dV, that is change in volume, should be equal to 0, and change in heat should be equal to 0. Therefore, from first equation we can write du equal to 0. It means that u equal to constant. Derivative of internal energy equal to 0. It means that internal energy is constant. Thus, the internal energy of a system remains constant in isochoric adiabatic process. Second is Helmholtz free energy, which is represented by F, and which is equal to U minus Ts, which is equal to internal energy minus product of temperature into entropy. As U, T and S are the state variables, F is also the state variable because it is equal to F. F has dimensions of energy. Now, according to first and second law of thermodynamics, we have the equation, directly equation घेतलेला आहे इथं, du equal to T ds minus dw. Why it is taken as dw? बघा या ठिकाणी du इक्वल टू आपल्याला इक्वेशन 2.9 इक्वेशन काय म्हणते, TDS मायनस PdV, and we know that PdV represents the work done, that is pressure into change in volume, that is represent the work done. म्हणून या ठिकाणी घेतला dw, TDS minus dw. If the system is maintained at a constant temperature by exchanging heat continuously with the surrounding, if the system is maintained at a constant temperature, it means that the heat is continuously exchanging by the system and surrounding, but in this process the temperature of the system suppose remains constant, then we can write TDS equal to dTs, because in this case temperature remains constant. Therefore we can write temperature after derivative. देअरफॉर डेरिव्हेटिव्हच्या आतमध्ये पण आपण लिहू शकतो बिकॉज इट इज कॉन्स्टंट, त्याच्यामुळे काहीच फरक पडणार नाही, म्हणून दिस कॅन बी रिटन ॲज DTS. देअरफॉर अबव इक्वेशन कॅन बी रिटन ॲज DU इक्वल टू DTS मायनस DW. देअरफॉर D ऑफ U मायनस TS, DTS लेफ्ट साईडला घेतलं आणि डेरिव्हेटिव्ह बाहेर काढला म्हणजे मिळणार आपल्याला D ऑफ U मायनस TS इक्वल टू मायनस DW. and we know that U minus TS is the Helmholtz function, that is equal to, this can be written as dF equal to minus dW. Now we have the equation dF equal to d of U minus TS, therefore dF equal to du minus TdS minus S dt. Therefore we get du equal to TdS minus PdV. वी हॅव द इक्वेशन DU इक्वल टू TdS मायनस PdV. हे इक्वेशन वरच्या टाकलं तर काय मिळते आपल्याला, DF इक्वल टू मायनस PdV मायनस SdT, मायनस PdV मायनस SdT. दिस इक्वेशन गिव्स द चेंज इन हेल्महोल्ट्ज फ्री एनर्जी इन टर्म्स ऑफ फोर थर्मोडायनामिक व्हेरिएबल्स प्रेशर, व्हॉल्यूम, टेम्परेचर अँड एन्ट्रॉपी ड्युरिंग द रिव्हर्सिबल प्रोसेस. नाऊ याच्यामध्ये कंडिशन बघू फॉर रिव्हर्सिबल आयसोथर्मल प्रोसेस. Now suppose the process of changing one state to another state is suppose isothermal process, and we know that in the isothermal process temperature remains constant, therefore change in temperature should be equal to 0. Therefore above equation can be written as dF equal to minus PdV, therefore PdV equal to minus dF. Thus the work done in reversible isothermal process is equal to the decrease in Helmholtz free energy. We know that PdV is the work done on the system or by the system. Therefore change in work done, that is PdV is the change in work done equal to minus dF. Minus dF means negative of change in Helmholtz function, that is there is a decrease in Helmholtz function. And suppose second condition is for isothermal isochoric process. We know the isothermal process temperature remains constant, it means that dT equal to 0, and isochoric process volume remains constant, it means that dV equal to 0. Therefore dF equal to 0 and we get F equal to constant, it means that in this process Helmholtz free energy remains constant. Third thermodynamic potential is enthalpy, which is represented by H. Therefore H equal to U plus PV. As U, P and V are the state variables, therefore H is also the state variable which is depends on the state of the system. H has dimensions of energy. If the system undergoes an infinitesimal reversible process, रिव्हर्सिबल प्रोसेस म्हणजेच काय, जे रिव्हर्स होऊ शकते. सपोज चहाचा कप गरम केला आणि ठेवून दिला तर थोड्या वेळाने काय होऊन जाणार, तो पुन्हा थंड होणार, म्हणजेच काय नॉर्मल टेम्परेचरला येणार, म्हणजेच रूम टेम्परेचरला येणार. ठीक आहे, म्हणजेच काय इन्क्रीजिंग टेम्परेचर अँड डिक्रीजिंग, दिस इज द रिव्हर्सिबल प्रोसेस. त्याच पद्धतीने सपोज फॉर इन्फायनाइटेसिमल रिव्हर्सिबल प्रोसेस then change in enthalpy can be written as dH. We have the equation of enthalpy H equal to U plus PV, therefore dH equal to du प्लस, आता या ठिकाणी प्रॉडक्ट आहे प्रेशर आणि व्हॉल्यूमचा, तर प्रोसेसमध्ये प्रेशर पण चेंज होते, व्हॉल्यूम पण चेंज होते, म्हणजेच काय बाय किपिंग प्रेशर कॉन्स्टंट डिफरन्सिएशन ऑफ व्हॉल्यूम प्लस बाय किपिंग व्हॉल्यूम कॉन्स्टंट डिफरन्सिएशन ऑफ प्रेशर, म्हणजेच मिळते आपल्याला du प्लस PdV प्लस VdP. therefore du इक्वल टू बट वी हॅव द du इक्वल टू TdS मायनस PdV. वरच्या इक्वेशनमध्ये टाकलं तर काय मिळते आपल्याला dH इक्वल टू TdS प्लस VdP. And for reversible isobaric process, now in isobaric process pressure of the system remains constant, therefore change in pressure should be equal to 0. Therefore our equation becomes dH equal to TdS and which is equal to, we know that TdS according to second law of thermodynamics, TdS equal to amount of heat absorbed by the system or released by the system, that is equal to dQ. Thus for an isobaric process the change in entropy change in enthalpy is equal to the heat absorbed, that is change in enthalpy in isobaric process, change in enthalpy is equal to the heat absorbed. Now second condition for an isobaric adiabatic process, isobaric means dP equal to 0, adiabatic means dQ equal to 0, म्हणजेच dH equal to मिळणार आपल्याला 0, म्हणजेच H equal to constant. It means that in isobaric adiabatic process enthalpy of the system remains constant. आणि फोर्थ थर्मोडायनामिक पोटेन्शियल आहे गिब्स फंक्शन, which is also called as Gibbs free energy. Gibbs free energy, this is the defined by the equation G equal to U minus TS plus PV, किंवा याला लिहिला जाऊ शकते G equal to H plus PV, F plus PV, because F is the F equal to U minus Ts. Therefore, G equal to F plus PV. This is the relation between Helmholtz function and Gibbs function. From equation we have the H equal to U plus PV, G equal to H minus Ts, and G equal to G plus Ts. Therefore, H equal to G plus Ts. Therefore, enthalpy equal to Gibbs free energy plus latent heat, because T product of temperature and entropy. This is called as the latent heat of the system. Now we have the equation G equal to F plus PV. Therefore, for an isothermal process, TDS equal to आयसोथर्मल प्रोसेसमध्ये काय टेम्परेचर कॉन्स्टंट असते, म्हणजेच लिहिलं जाऊ शकते TDS कॅन बी रिटन एज DTS. अँड फॉर अन आयसोबॅरिक प्रोसेस DP इक्वल टू 0. देअरफॉर DH इक्वल टू TDS. देअरफॉर DH मायनस TS इक्वल टू 0. Therefore, DG where H minus TS is the Gibbs free energy function. Therefore, DG equal to 0. Therefore, G equal to constant. Therefore, isobaric process मध्ये Gibbs free energy remains constant. याचं पण युनिट काय असते, एनर्जीचं युनिट असते. That is Gibbs free energy remains constant in an isothermal adiabatic process.